Okay, so initially let's view a couple of slides. These slides will be available on the e-learning platform. So we'll be using linear algebra to solve Monopoly, the board game, not the problem in economics, but the board game. So to start, let me remind you about the model we have talked about during the last lecture, which was called Markovian-Weber model. And effectively, we will treat Monopoly in exactly the same way as we treat Weber in this model. So what are the important ingredients of the model? Well, we assume that the weather can be only in two states. It can be either sunny or rainy. Well, today is neither sunny nor rainy, but our model is kind of very simple, and it looks like it will start to rain. So we could classify today as a rainy day. So when we are today, we know exactly, well, the day we're having this live lecture on is not exactly, as I have told you, nor rainy nor sunny, but we could say that, well, I assume that this weather is 100% rainy. So we know that with full precision that today we are in this state. And our model tells us that if today is rainy, there is 80% chance that tomorrow will be rainy, or 20% chance that tomorrow will be sunny. So if we imagined us today just a single particle, our particle would either stay in the same state 80% of the time or move to another state, sunny weather, 20% of time. But when we are using linear algebra tools as the way we're using in this slide, we imagine that we have infinite number of particles. And we simply keep 80% of that infinite number in the rainy state and move 20% into the sunny state. So effectively what we're counting particles in each state, in each either sunny or rainy state. And basically, well, yeah, we're just counting particles, and each time we iterate, basically we make another move of a particle, because, well, today we are here, but there is a chance that tomorrow we will move either to sunny or stay here. And the day after tomorrow, we will have 20% of our original particles moving from sunny state, either back to rainy or staying at sunny. And, well, those particles which have remained in rainy state would have 80% chance of remaining or leaving that state. So effectively, we could apply these rules over many days and move those infinite particles from one state to another simply by following these rules. And this model is well encoded by using linear algebra tools. So basically we encode the transition probabilities we see here in this picture as a matrix. And here the column is so-called from state. So our first state, let's say, is sunny, our second state is rainy. So the first column encodes the transitions from sunny state, so 60% chance to remain. So the source state is the first state, and the destination state is also first state. Then there is 40% chance to move to a rainy state, which is our second state. So our source state is rainy because it's the first column, and our destination state is rainy because it's the second row. Similarly, here our source state is rainy because the column is second, and our destination state is sunny because the row is 1. And, well, this one is both from moving from rainy state to rainy state because both column and row is number 2. So basically, if you would read this matrix, diagonal elements give you the probability to stay in the state you were in. Basically, it's telling the fraction of particles which remain in the state if we consider infinitely many particles. And simply to calculate fractions of the particles remaining in every state, we simply multiply our transition matrix by so-called state vector. And well, as of the recording of the previous lecture, weather was sunny, so our initial state vector was 1, 0. So it meant that it was 100% sunny and 0% rainy. Today, it would be vice versa. Our first number would be 0, and our second number would be 1, because today is a bit more rainy. And if we would want to generate the forecast, we could simply multiply our original state vector by some power of the transition matrix. So effectively, what we will be doing today will be very similar to how we have solved, well, not solved this model, but basically generated weather forecast during the last lecture. We will not start with monopoly from the start, because, well, it would be a bit too complicated. And let's first talk about some simple games, a bit more simpler games. So the simplest game, which is similar to monopoly, would be simple linear game. So basically we start at square 1 and we need to get to a square 9. So we have simple linear track. We roll single standard 6-sided die. And basically we are square 1. We rolled the die. We, let's say, got a result of 3. So we move 1, 2, 3 steps forward. And basically the game ends as soon as we reach 9th square. If we go over that square, it's also fine. We treat that. We basically just land at square 9. So okay, the question of this simple game would be when the game will end. So let's try answer this question by doing some Matlab. Okay, let me switch to Matlab. So I'll make a separate directory. New game. For the linear game. Okay. Behind this one, and yeah, this will be solving linear game. So, okay, what ingredients do we have? We have that there are 9 squares in the game, and that we have 6-sided die to roll. So let me start by building template for the roll. So how does this template look like? So I'll name it like that. Well, so let's encode our roll like that. So we can roll numbers simply from 1 to 6, but the probabilities to roll them are exactly, well, equal. We can roll each face of a 6-sided die with a probability 1/6. So what I need here is not vector from 1 to 6. Instead, I need a vector of 1s, which would be of size 1 by 6. So 1 row, 6 columns. And I need to divide this by 6 to get a template. So basically, let me run the script. And how does my variable look like? So this means that there is 1/6 chance to move 1 square forward, 1/6 chance to move 2 squares forward, 3, 4, 5, and 6. In Monopoly, we will be rolling two standard dice, two six-sided dice, so our template for the roll will look a bit different. But in this case, we just have 6 numbers, all of them 1/6, well, just because this encodes our dice roll, and it simply encodes the probabilities to roll that many squares. So now I need to use this template to actually build the transition matrix. And I'll be using a trick from previous lecture I have shown you in the lecture. So, okay, what I need to do here, I need to build banded matrix. And there was an example how to do that in the lecture. And yeah, basically I need to use spdx function. I can open up its documentation in Matlab. You can do it like that. You can use either help if you want to get output in the command window, or you can use doc, the function name. And if you use doc, it opens up Matlab Online help. And basically, yeah, I guess I already know that I need this one. So it creates m by n sparse matrix. Well, sparse, it does not matter what sparse means in our particular case, but this matrix will be m by n, and yeah, output matrix S by taking columns of bin, our first input argument, and placing them along the diagonals specified by D. So okay, let me decode what that means. So here we will be building transition matrix. Let me name it very originally, simply transition matrix. What I need to use function full. It was present in the example. What it does, it converts sparse matrix into the standard matrix we're used to work with in MATLAB. Not only in MATLAB, in maths and so on. But okay, so now I need to use spdx. And first, well, I need to give it a matrix, which will be then shifted to lie on the diagonals of that transition matrix. So, okay, but I have not yet made that matrix because standard roll is just a vector, and I need to make a matrix out of it. So let me create matrix representing the same roll, and I need that matrix to be of the size 9 by 6. Why 9? Because we have 9 squares in our problem. Well, this is constant, so I guess I can use capital letters for constants, but it does not matter in this particular case. And how do I do that? Well, I need actually to stretch this standard roll vector over 9 rows. One way how could I do that is basically do standard roll and basically copy and paste this 9 times. Well, but I will not do that because it's manual labor. And we can do the same thing a bit more cleverly. I do not recall if I have shown you this function in the lecture. Oh, I guess I haven't shown you this function in the lecture. Okay, but I know that function, and it is called repmat. So let me go back to here. You probably see that it tells that it does repeat copies of array. So let me open up documentation for the repmat function. And basically what its basic usage is just passing some matrix or array or vector. I prefer calling them matrices and vectors in MATLAB, not arrays, but matrices and vectors, because it brings us a bit closer to the mathematics behind the things we're doing. But in general, we could call them arrays. And simply this would refer either to a vector or matrix or tensor or whatever other structure, arranged structure of numbers, which is some kind of table, one-dimensional, two-dimensional, or three-dimensional table. Does not matter. In all cases, it would be an array. Basically, just in our case, it's synonym for matrix. So, okay, what it does, it repeats, it creates n copies of A in row and column dimensions. So basically what it does, it takes matrix A. So let me close it. So if I do, let me open up window fully. So if I do rep math, let's say matrix 1, 2, 3, 4. So let's look first at matrix, how it looks like before repetition. It looks like that. Simply have 1 and 2 on the first row and 3 and 4 on the second row. And then if I do rep math of matrix, our matrix math, and I give it number 2, what it will do, let's see. And what it did, it created additional copies of math, and it made it so that there are 2 matrices on the, basically it created a copy to the left-hand side, right-hand side, then it added another row. So basically what it did the same thing as with math. So what does the number 2 tell us? It basically tells us that there are 2 times, we repeat math 2 times on the column dimension, and then we add, and that we have 2 rows along the row dimension. But in this case, our row is not just a single file of numbers, it just is a row of matrices. So if I do it like that, it's exactly the same as rep math. But what I need here is not to repeat along the column dimension, I need to repeat the vector standard role along the row dimension. And let me try doing that. Do I have this variable in my workspace? Oh no, I do not yet have a variable, so I will have to run the script. So yeah, okay, I need to comment this out too. So let me run. Now I should have standard role in my workspace. So yeah, and let me do it like this. So okay, let me go back to the documentation of rep math, and notice that another use is to give a list of numbers after rep math instead of giving just a single number. I can give multiple numbers. Basically, it describes how copies of A are arranged in each dimension. So if we go back to our math example, instead of writing rep math 2, we could tell rep math 2, 2, and then it will give us exactly the same. But if we tell this to give us 1 and a 2, what will happen? Oh, it will extend along the column dimension, which I do not need. So simply by experimentation, I figure out that I need to do it like that. So I need to pass number of repetitions along the row dimension first, and then I need to pass 1 so that Matlab would know that along the column dimension it does not need to do anything. So let's write this in our code, and we will be repeating our standard role. And well, Matlab quite intelligently suggests what I will be doing next. I will be writing n squares. And then I need no repetition along the column dimension. So it's quite strange that Matlab has guessed that I will be using n squares, but I guess it's reasonable because it's the only scalar value I have defined in my workspace. So I guess it makes a bit of sense. So let's run the script and let's look at our standard roll mat. How does it look like? And basically, well, it looks trivially. Its size is 9 by 6, exactly what I wanted. I wanted 9 rows and 6 columns, not something like if we would not pass 1, we would get a matrix which is 9 by 54, well, because it just repeated along the column dimension 2, but I need actually to have 9 repetitions along the row dimension and no repetition along the column dimension. So I'm giving just 1 to repeat that matrix just once, that vector in our case. So okay, let's, oh, we do not need to run this. We know that it runs already. And here I'll be making a transition matrix. So I need to pass to SPDX. And yeah, so I need to tell Matlab what kind of dimension of matrix I expect SPDX to be. And initially, well, I know that we have 9 squares. And to describe transitions from every of the 9 squares to every of the 9 squares, we need 9 by 9 matrix. But let's keep our code a bit more general. So basically, we could, if we wanted, we could increase the number of squares in our problem anytime we want. So basically, here I'm telling that I will want a matrix to be n squares by n squares, 9 by 9 in our particular case. Here, the second value, I need to give Matlab instruction on which diagonals I want to fill. Let me jump to this, make matrices. And yeah, when we're making banded matrix, our main diagonal is, well, 0th diagonal. So Matlab starts numbering diagonals from 0, and then positive numbers move to the right. So here we have 0th diagonal. This diagonal is the first diagonal. The diagonal below the main diagonal is minus first diagonal. Similarly, here we have minus second, minus third, similarly second and third diagonals. So in our case, we do not want to fill the main diagonal because after each row, we're making a step forward for sure. We're making at least 1 step forward. So let's jump here. So we will need to tell that we want to fill diagonals from first till, well, till the length of standard row. Well, I could give here number 6 because I know that I have 6 elements in this vector, but well, let's skip. Oh, it's okay. I guess I need to do that like this because standard roll mat is actually a matrix, and I want to have number of columns in that matrix. So I need to pass number 2 here, and it gives 54 because we have our previous matrix, which was created using this command. When we run the script, this one will give us number 6. So, and here we need to give, as our first input argument, we need to give the values we want to write into a matrix. The values we want to write into a matrix are stored in the standard roll mat. So, okay, let me split this code into multiple lines so that I would fit into the 8-character limit here. And basically, yeah. So this should build us a transition matrix. So let me run the script. I can do that by pressing key F5 or by typing script name into the command window. So let me do this time like this. It has run, and let's explore the transition matrix. And I will be doing that by using image sc function, which does plot images by default. So let me place this on the side, I guess. So what we see here, well, in this color map, it means that there is some probability to go from first square to second square, then to a third, fourth, and so on. Basically, if the more yellow squares are, the bigger the probability to visit that state. And if we have no probability of reaching certain square from certain position, it means that, well, we have magenta color, and it tells us that there is zero probability to reach those squares from that square. So let's say in this case, we can't reach first square from the third square, because we are always moving in this game. We are basically rolling the die and adding the number, and we can't roll 0 on the die. We can just roll numbers 1 through 6 because it's a standard die. So here I'm making one mistake already, and actually it's not a mistake. It's just the way I like doing things. So this transition matrix is not the same as the transition matrix I am giving here. It's actually a transposed matrix of this one, because I like my rows telling the source state and my columns telling me the destination state, because it's more natural for me to tell Matlab or any other programming language that I want to know probability, transition matrix, I want a probability to go from the first state to, let's say, third state. It's more natural for me to do it like that. The original transition matrix we will need to use in our linear algebra calculation. Let me call it proper transition matrix, is a transpose of the transition matrix I have written. So we would write it like that. And then we would need to tell Matlab first, we would need to tell the destination position, and then, destination state or destination square in our particular case. And then we would need to tell the source state. So basically, if I would plot, let me quickly plot those two side by side. Okay. Yeah. Let's try doing like that. Well, I'll tell Matlab to create a figure. I hope this works nicely. So I need to do image sc here, transition matrix. Okay, yeah, here I need to write proper transition matrix, and I guess this should be enough. So yeah, Matlab has plotted them side by side, and basically you can see that it's simply, I have just transposed. Here is the way I have written transition matrix, and this matrix is actually what we need when we will be doing various calculations using linear algebra tools. So Matlab complains about something, but it seems to be related simply to the way graphical interface is done in the web application. It's not an error in my code, just the way web Matlab works. So okay. So, but I have forgotten one thing we actually need to do. We need to test the transition matrix, so that transition matrix would be actually proper transition matrix, and what the condition there is. So let's jump to the lecture slides And let's go to the Markovian. Oh, I have it open in this lecture slide. Notice that columns of the transition matrix, as written in the slides, sum to exactly 1. Why do they sum to 1? They sum to 1 because something must happen. You must either stay in the certain Weber state, or you must move to another Weber state. Similarly, in our game, we must move to one of the 6 squares behind us, which square will depend on our role, but we must do that. So our row, not columns in this example, because, well, in my case, it will be sum not over columns, but it will be sum over the rows, and the sum must be equal to 1. So let me first do that in the command window. So sum transition matrix, over which dimension it sums by default. By default, it sums over the columns. So I need Matlab to tell Matlab to sum over rows. Oh, I guess I need to give number 2. And I know that it's summing over rows because it gives me a column vector as an output. So I know that it took numbers from first row and got this number, took from second row, third row. And notice in the fourth row, we have sum which is not 1. So it's actually 0.83 and so on, 333. This means that why this happens? This happens because, well, let's look at our transition matrix, and I guess it will be easier to look at by using variable editor. So we see that, well, here, if we would extend our matrix, we would get numbers running outside. So effectively, we are from the third square, we can reach as far as 9th square. But from the 4th square, we can, in theory, reach non-existent 10th square. So we are losing probability of reaching 10th square. Similarly, from 5th square, we're losing probabilities to reach squares 10 and 11. So we need actually to make some effort to fix that. So that basically increase the probability of reaching square 9 at expense of the later squares, because they do not exist in our game. So let's do exactly that. So, well, let me, before fixing the error, let me write a test. And tests in Matlab can be written by using function assert. For function assert, I need to give some condition which must be true for the program to proceed. So my condition will be all. Well, let me write condition as, well, test condition. I need sum of the transition matrix elements over 2 to be equal 1. And I am not testing for equality because we are using floating point arithmetic. And in that case, we can have numbers very close to 1, but not exactly 1. So instead, I'm testing if the difference between the sum and a 1. Well, I guess let me make the mistake first, and I will correct it a bit later on. So, okay, this is my condition. Let me add parentheses to emphasize that this is actually a Boolean variable. And here I need, let me do it here. I need this to be true for every row. So I'm using function all. So just to remind you, function all returns you true only if all elements in the vector I'm giving it as an input are true. If at least one value is false, function all will give logical 0, which is false. So, okay, now I need to assert test condition. And I need to give some message which will be shown as error. So I'll be writing some of the rows do not sum to 1. So this error should be triggered as I run the script now. So let me clear the window and let me run the script. And notice that error using main script, sum of the rows do not sum to 1. When I click this line, it moves me to my assertion. So this is a way how to handle errors in Matlab without resorting to writing your ifs, some print statements, various ways to quit, to stop the execution of the script. Simply to use assert function, give it some condition, and well, write some message for the person running the script, so the person would know what's wrong in his calculation. So in my calculation, I know that some of the rows do not sum to 1. So let me try fixing it. So what I need to do, I need actually to take values in the 9th column. Well, not 9th column, but n squares column, which is 9th column. And I need it to act as a way to balance my matrix. So basically, I will be summing over. Oh, this suggestion is not correct, Matlab, but thank you. So I will be summing. What I will be summing? Yeah, I will be summing over all rows, and I will be summing over all columns. Well, here I can use not n squared, but and. I guess it will be a bit faster. Here I will be summing over all columns besides the last one, I think. So let's open up. So what my sum will effectively go over all rows, but it will go only up to 8th column. So this will make sure that the value in the 9th column changes value so that the respective row sums to exactly 1. Well, not exactly 1 because we are doing numerical computation. So, okay, and this should do exactly that. So here I'm telling Matlab to sum over all rows. So effectively, let me show you what this thing does. The command window. So my transition matrix looks like that. My full transition matrix. And then I tell Matlab to take all rows and take all but the last column. So from the first column till the column which is end, the last column minus 1. So in our case end is 9 and 9 minus 1 is 8. So I should see all the matrix with this row truncated. So yeah, this is exactly what happens. And if I try to sum like that, I will get some values, which is a sum over every row in this truncated matrix. So let me hide this one. So I need to tell Matlab to sum. Now this should be fine. So let's try running it. Okay, and Matlab does not complain. It seems that it's, in this particular case, the problem I have thought of, which will be important, seems to be bypassed, which is kind of strange. Because when you're adding numbers, let's say, let me try an obvious thing. Add 1/6 6 times. Oh, it's 5 times. looks like 1, but I believe it's not exactly 1. So this is kind of strange because, well, why this happens? This happens because 1/6 can be properly represented as a number in computer memory because we have finite amount of digits. So we have finite amount of digits. We can't even represent the number. Well, it would be 16666, and 6 would repeat till infinity. So we can't represent 1/6 even if we use decimal arithmetic. In binary arithmetic, some numbers which can be represented in decimal, what those numbers are, let's say 1/10 can be represented quite well in using decimal arithmetic, but it will be hard to represent using binary arithmetic simply because of how the numbers are encoded in binary. So what I did expect from the assert function that it would actually return 0 value. But it seems for Matlab that everything is fine. Instead, when checking the value of, you shouldn't do it like that to circumvent the problem I've shown you in command window. So let me go back to the command window once again, and I will show you how to actually solve that, how to, in this case, to get true, not false. You need to do it like that. So you basically move 1 to the other side of equation. Then you take absolute value, check if it's smaller than some small number. Now it's fine. You can actually try decreasing the number. So here it's false. So we know that the error is around 10 to the power of minus 16. And yeah, it's around 10 to the power of minus 16. In my case, I know that I will not be dealing with extremely small numbers. So I will be doing it. I will be using, let's say, 1 to the power of minus 6. Check. And this test should be a bit more robust in regards with how floating point real number arithmetic works behind the scenes in Matlab. So okay, so yeah, so let's run the script and see if now everything is fine. Yeah, get no assertion errors. So let's look at the transition matrix. Yeah, so we see that probability to go from square, these probabilities are low, and these probabilities are more or less large probabilities. So it's pretty much clear. Well, these probabilities are large, so that because, well, from the 9th square we no longer move anywhere, so there is 100% chance to remain at that square. From 8th square we can move only to the 9th square because all other 10th, 11th, 12th, and so on squares are not available to us. Instead, we stay in the 9th square. So these are inflated because we do not allow the game token to move outside our game board. So, okay, so what question did we need to answer? So we need to answer when the game will end. Okay, let's jump to Matlab. When the game will end. And we know that, well, this game will be exactly, well, not exactly, but no more than 9 rolls, I guess. Well, actually, it will be no more than 8 rolls because we're starting square 1, and even if we roll all ones, by the 8th turn, we will move to the 9th square because 1 plus 8 times 1 is 9. So I'll be writing a 4 cycle because I know that I need to make exactly 8 rolls. And what I'll be calculating, I will be calculating fraction of those infinite particles which have reached 9th square after a given roll. So finished particles. Well, we can omit particles and simply do it like that. So I'll be pre-allocating vector, so Matlab would not complain me about it. And I know that I will be making n squares minus 1 more. So here I can replace 8 with length of finished. And I need to assign some value to finished. And what value would that be? That value will be transition matrix. Oh, I need to actually translate transition matrix to, well, my transition matrix into a proper linear algebra transition matrix. So I'll name proper. And what I need to do, I need to do transpose. So I'll be doing just transpose. It does not matter if I omit this dot, because I'm not dealing with complex numbers, but just for propriety, let's add the dot. So okay, I need to add semicolon here. So I need actually to I guess to define my initial state vector. So my initial state vector will be very like this one. That will be 1 by 9, 1 by n squares, because I need to encode the probability of vector of particle being at certain particular square. And I need actually for the initial condition to place all the particles in the first square. So let's look at this one, to what it evaluates. State vector, initial state vector will look like this. So all the particles are in the first square and there are no particles in other squares. So let's now finish this up. So I'll be updating state vector using the proper transition matrix. And I'll be using matrix multiplication because, well, here we have not ordinary scalar multiplication between elements or element-wise multiplication, but we have matrix multiplication. So if it would not be matrix multiplication, we would not have linear algebra here. So I'll be doing matrix multiplication. It's the default operation of the multiplication of the asterisk operator in Matlab. And well, the number of particles which finished is given by the number of particles in n squares in the last square. So let's try running this one. So let's do it like that. Okay, len. Oh, it's not length. It's length in Matlab. So I fixed this error. Oh, okay. So Matlab complains about the incorrect dimensions for matrix multiplication. So recall that, well, when you multiply matrix by matrix, number of columns in the first matrix must match number of rows in the second matrix. And here I have n squares by n squares matrix. And here I have 1 by n squares matrix. So inner dimensions of those two matrices do not match. So I need actually to change this one into n squares 1. Now, this one is n by n, and this one is n by 1. We can actually write a comment here. So this one is n by n times this one is n by 1. So here we see that these inner dimensions match, so we can actually do the multiplication now. So let me delete the comment and let me try running the script again. Now it does not complain. Let me plot. Finished. How does finished look like? Well, strange that Matlab does this. Why does Matlab does this? Okay, it's strange because, well, the plot somehow is missing large chunk of the. Yeah, we could try. What we could try? Well, let's open up the side panel and let's finish this here. Let's try. And okay, it seems that Web Matlab does not like me much today. Why does it? Well, okay. So I guess Web Matlab complaint is not very friendly today. But if I give it a different style, no, it still complains. Oh, okay. It does not want to plot straight lines today. So let's take a dotted line instead. So we see that 0 games end on the first turn, 40% of the game will be ended by the second turn, more than 80 over third turn, and so on. So the game is more than 50% likely to be ended by third turn. This could be one of the answers we're giving. So yeah, let me. Another answer we could give 2 is actually, yeah, like finished like that. And another answer we could give probabilities to finish on a given turn. I'm adding 0. Why I'm adding 0 here? Because when diff takes vector of some length, it returns vector which is one element shorter. So if I have finished here, and if I take diff finished, it returns me a vector which is one short. So if I add 0 before, it will give me vector which is exactly of the desired length. So okay. Okay, this is interesting. So this one should now give me, I guess, another plot. So let's run the script. Oh, okay. Let me set this style so the figures will be a bit nicer. So, okay, let me run this again. So yeah, now we see the probabilities to end exactly on the same turn. So there is over 40% chance to end either on the second or on the third turn. Then the probabilities actually diminish. So I guess this is it for the linear game. So let's move on to the, well, to the solving of the looping game. I'll try to go a bit faster because now we know almost all the basics. So, and we will be reusing a lot of code. So what is the difference from the linear game? From the linear game, the difference is that our track is actually looping. So we have 8 squares and we move, well, basically in a loop. And there is no end to this game. We're just moving in a loop. Let's still roll a single 6-sided die, and the question will be, what's the probability of visiting square on the first turn, on the third, on the 100th, and after infinite number of turns. So I'll be doing it like that. I'll be copying the code. Let me open up the command window and okay. Okay, I guess now it should be a bit better. Okay, let me fix here a looping game. And squares, well, there are 8 squares in our particular case now. So template for the roll remains the same because we need the same, we are rolling the same 6-sided die. Transition matrix, well, things start to change from the transition matrix. So let me comment out some code. I'll keep the test and I will comment out everything after it. So we need actually, let's run the code and examine how does the transition matrix look like. So, notice that we still have so-called absorption at the last square. And in this case, we do not need to absorb the particles at the 8th square. We instead need to allow them to move forward, well, to loop back. And how do we do that? Well, we cheat a bit. We do not need this line. We do not need absorption, but this will actually ruin our matrix. Some of the rows do not sum to 1. But we can make, well, our SPDX, it creates banded matrix. So it means that effectively those bands continue beyond the matrix we are defining here. So the trick would be to ask SPDX to produce not n by n matrix, but to produce n by 2n matrix. So let's see what happens now. When I run the script, oh, I haven't added plotting of the image as C. So yeah, transition matrix. So how does it look like now? Why it hasn't changed? Okay, let me close the window. How does my transition? Well, it should look. Somehow Matlab doesn't like me today. Well, now it's fine. So our matrix is now 8 by 16, and we see that, well, the bands we have defined, the diagonals, continue outside the range we actually need. And we need actually to move those values from the 9th row till 16th row. We need to cut this 8 by 8 piece and move it to the first 8 by 8 piece. So what will be happening here? We will be redefining transition matrix. We will be taking original 1 by n squares 1 by n squares. So recall that this encodes only this triangle which describes transition until the 8th square. And now we need to make the loop. And the loop, well, think about what happens when we are at square 8. If we roll 1, 8 plus 1 is 9. But instead, in our numbering system, we are moving back to 1. So we know that 9th column corresponds to a first column. If we roll 2, 8 plus 2 is 10. But in our calculation, 1, 2 steps forward is number 2. So its 10th column corresponds to the second column. So on 11th to 3, and so on 12, 4, and so on. So effectively what we will be doing here, we will be adding values from rows n squares plus 1 till the end. Okay, sorry, first dimension is actually rows, so we need to keep exactly the same rows because source square does not change. Destinations, we need to loop the destination squares, and this does exactly that. This picks rows from, in our case, from the 9th column till the end, till the 16th column, and it makes so that 9th column adds values to the first column, then 10th column adds values to the second column, and so on. So yeah, effectively it takes this lower triangle and adds this to the matrix. So we'll see what happens after I run the script. So let me close figure. We run the script and let me plot the figure. So what has happened? This triangle was in the rows from the 9th till 16th. And basically what's now happening is that it is moved properly to the destination numbering which we are using in here. So effectively we know that we can move from the 8th square to the 1st, 2nd, 3rd, 4th, 6th, 5th, and 6th. We can move to all squares from the 8th square. So this makes the transition matrix. And actually, the biggest challenge in this lecture is not the programming itself. There are a few new functions I have shown you, but in general, the biggest challenge is to build a proper transition matrix, and then everything else simply follows. But we will still see one function which we will have to use for monopoly next. So okay, so now everything, the test seemed to pass. Okay, let me close the window. So I still need to translate my transition matrix into proper transition matrix. So I need to uncomment. What's kind of strange that in Matlab I can easily comment out things by pressing Ctrl+R, but somehow I'm unable to uncomment them easily. And in my workflow, I like to comment and uncomment things quite often. So it's a bit of annoying. So this one will translate into a proper transition matrix, and we do not need this part of the code from previous example. So let's ask, well, we actually need the code. It will be still useful. We just need to change it a bit. So the question is not when the game will end. The question is how likely we are to see a player visiting 8th square after first turn. So yeah, let's define the state vector. And basically, after first turn, the state vector will look like proper transition matrix times state vector. And we can add f print F probability to be eighth square after first turn is 0.3. No. This should print out percent sign because in fprintf percent is a special symbol. This one should give me a percent sign. So let me, and I care about being at the eighth square, and I need percents, not fractions. So let me run the script and let me see the output. So probability is 0. So it's trivial because 1 plus at most 6 is 7, and we can't reach eighth square. How likely we are to see this square on first turn? Our next question is about third turn, as far as I believe, as far as I remember. So we can reuse exactly the same code, and I'm making changes as I go. So this one will change, and yeah, I need to remain after third turn. So to make 3 turns, we need to raise matrix to the power of 3. So how we would make without the power those transition? We would effectively have to do it like that. So this one would make the first turn, this one would make the second turn, and this one would make the third turn. If you're actually thinking about matrices, as I have suggested in the lecture, thinking about them as transformations from one space to another, so we could think about as this being transformation from the initial space. We could have any other arrangement of particles here, but we have now this arrangement. So this makes transition from the space which corresponds to a first turn to another space which corresponds to a second turn. Would actually do it like that, as we did in previous, and then run this command again. This would now be as a vector in a space of second turn, and our result will be a vector representing some position in a space for the third turn. So effectively, you can look at this like that. So when you do three multiplications, this converts us from the initial state to from the initial space to a space corresponding to the space existing after the first turn, this one after the second turn, finally this one after the third turn. But it's a bit more convenient simply to raise to the power 3. So let's do it like that. Oh, we still need to have multiplication here. So our matrix is square, so if we raise it to power, we still get a square matrix back. So this one is changed. So let me add another after 100th turn. So the only thing I need to change here is actually do it like that. And actually, to be a bit more optimal, I could write a for script. So for after turn, I know that I will be after first, third, and 100th turn. So after given turn, yeah, to the power of after turn. So yeah, this seems to be fine. Okay, I need actually to change this too. And I need to give the number of turn. So I can delete this code now. On nth turn. So let's now try running this, and let's examine the output. Oh, okay. I haven't added a new line symbol here. So let me rerun this. Okay. Doesn't seem that Matlab listens to me well. So, okay. I see that %d. Why it's %d? Oh, I guess Matlab treats it as, oh, okay, the order is incorrect. So let's do it like that. Let's run now. So, okay, after the first turn, there is a chance of 0. After the third turn, there is a chance of 11%. And after the 100th turn, there is a chance of 12.5%. So we also need to answer what's the probability after infinite number of turns, and basically we can't do it like that, despite inf actually being an actual thing. Well, I guess we could try doing that if that works in Matlab. Matlab is smart enough, it will actually do that, but I would think it will not work like that. Yeah, doesn't work. It gives not a number as an output. So we can't do it like that. Well, what does it print out if we give it to fprintf, just for the sake of, oh, not none, inf. Oh, okay, it prints out simply inf. So we can actually add a clause if after turn is equal to infinity. Well, I need actually to check one thing. So I get infinity by dividing 1 by 0. And does a equals infinity? Yes, it does. Why I'm checking that? I'm checking that because in other languages, sometimes infinity does not equal infinity. In Matlab, it seems that everything is fine in this regard. Oh, I guess, is there a nicer function? Yeah, there is a function, is_inf, which will work. This one is not very elegant, so let me do it in a bit more elegant way by using function. And I know that I do not want to continue to do this. Oh, I want to continue because I want to print out the result. So, okay, I guess I will have to use if-else statement. And this will happen if after turn is not infinite. For the infinite, we need to actually use a thing which we have also covered in the lecture, but it's slightly more advanced topic. It's related to the problem of eigenvalues and eigenvectors. So yeah, matrices are transformations, and we in physics often care about things which persist. And in this case, we also care about things which persist because we care about what happens at infinity. So for anything meaningful to happen at infinity, we need to have some kind of persistence in our model, in our system, and whatever. Basically, in linear algebra, you take some matrix to figure out vectors which persist. And you are solving basically eigenproblem, so-called. Here, V is a vector which you want to persist, and lambda is some value, which is called eigenvalue. V are called eigenvectors, and lambdas are called eigenvalues. So, yeah, a bit sore throat from talking too much. So, okay, let's continue. So we want to find some vector, some state vector, which actually persists. And for that vector to persist, we need to have eigenvalue of 1. eigenvalue of 1 would simply mean that that vector is not deformed, nor it doesn't stretch, it doesn't change its orientation. And why it can't stretch? If that vector would stretch, it would mean that we are losing particles from the system. And here we are not losing any particle in the system. We always have the same number of particles in our system. So the only eigenvalue we're interested in the eigenproblem is one with lambda equals 1. So how do we actually do it? Not by hand, obviously, but how do we actually solve eigenproblem in Matlab? Well, we are using a function called eig. And let's actually use that function. So I know that, well, in the slides I have told you that V is a matrix of eigenvectors and D is a diagonal matrix of eigenvalues. So first I have eigenvectors, then I have eigenvalues. So let me do it like that. Eigenvectors, eigenvalues, eig of not transition matrix, but proper transition matrix. Now, okay, so I care about eigenvalue, which is exactly 1. So I need some way to find that. So mask eigenvalues, well, I could do that, but recall that we can't do that because, well, we are doing linear, sorry, not linear, we are doing real number arithmetic using floating point numbers. And in some cases, numbers which are 1 will not be 1. They will be very close to 1. So we need instead use the trick I have used in the test condition. I can actually do it like that. I can copy it here. And I will replace the sum with eigenvalues. And what I need to do, well, let's do simply the mask. So mask here will be a vector of true or false values. So, well, actually, let's try running this in command window. Do I have proper? No, I do not have proper transition matrix defined. So let me comment this thing out, run the script, and then comment. Control Z works. If I do that immediately after, so now I can hopefully do that. Okay, what does the mask look like? Oh, okay, I have forgotten one thing, that eigenvalues is a diagonal matrix with eigenvalues on the diagonal. And I can use function diag, which I have shown you in the lectures, to get the values on the diagonal. So, and I care actually only about the position of, well, on the diagonal. So I can make my eigenvalues matrix into a vector by taking values from the diagonal using function diag. Now I will subtract 1 and check if the absolute value is small. If it is small, we'll already see, well, that the first value is 1. But, well, whatever. Let's fix the code. And now mask should contain, okay, it contains 8 values because our matrix, our matrix, I guess, is, yeah, it's 8 by 8 because we have 8 squares. So, okay, what does this mask tell us? Mask tells us that the first column in the eigenvectors matrix is our stationary vector. So stationary, I'll call it distribution eigenvectors, and I need to take the correct column. So mask will give me probably the correct column. And okay, let's try running the script. Hopefully it will not break. Okay, why does it print out? Oh, I guess it reuses value from the previous cycle when printing out after nth term. But it's actually the correct answer. We will see it a bit later on. So now I care about how my stationary disk looks like. And okay, it looks like pretty strange. But notice, let's go back to the lecture slides, that it is customary to choose such eigenvector that its squared will be exactly equal to 1. So what we need to do actually to turn that stationary vector into proper stationary distribution is to actually square it. But square it not in a matrix way, but square it in the element-wise way. So why do we need to square that? Well, we know that stationary distribution must sum to 1 because every particle needs to be somewhere. So this one actually transforms into the stationary distribution. And then after a given turn will be value from the stationary distribution, eighth value, because it gives the probability to be at the eighth spot, eighth square. So let's run the script again. The output will not change because actually, oh, okay, what's wrong? Line 47. Oh, okay. I needn't do that. I needed just to copy values to the after given turn value. So let's rerun, and we see that nothing changes from infinite turn to 100 turn. And why? Because, well, 100 turns is enough to reach the stationary behavior. And the stationary behavior, if we actually plot it, I'm sorry, looks like that. Well, still, Matlab has its own, plays its own games on me. So let me do it like that. So we see that it's, well, it looks approximately equal to 0.125, but it's, well, the fluctuations are very, very small. As you can see, these numbers are pretty close to that value. What if I use bar chart? Oh, see that all values, but okay, all values are approximately equal, well, to something over 12. And that something over 12 is actually value 1/8, which means that every value is exactly likely to be there, to be at any spot. Well, and why these values are equally likely to be at any square? Simply because, well, we do not differentiate them from the other squares. So I now see that our lecture time is actually ending, and we are just moving into Monopoly. So once again, let me remind you that, well, this video will be recorded and put in YouTube. If you are tired and you want to move to do something else, or if you have to leave, you can freely do so at any point, and you will be able to watch the video later on at your own leisure. And basically here we would move to a bit more complicated, to our main problem. Basically, I believe the solution should be more or less quick, because we already have figured out all from the programming perspective what we need, and also we have figured out everything from the mathematical perspective tools which we will be using to solve Matlab. So I guess if you want, you can simply leave and move on to do your things, and later on come back and watch that video if you want. And just as a reminder, so there will be a short quiz based on the things about maths and Matlab we have talked about in this lecture, and I hope to put it online somewhere by the evening today, as well as all of my code and slides. and the video on e-learning platform. So if you want to leave at any time, you feel free to do so.